Okay, let's get started. Those of you who are happy to do so, please turn on your video. Everyone else, please be ready with the thumbs up, thumbs down icon to let me know how things are going. And let's get to work. So today we're going to be working through some questions in the extra review problems, which were posted recently to prepare for the upcoming midterm. It's going to be somewhat similar to what we've been practicing already. We are going to be presented with a bunch of series, and we're being asked questions about them, mostly about their convergence. There are also questions about how close the partial sums are to the actual answer. And we have two main tools to understand that. We have the integral test, and we have the alternating series error estimation. Okay, so let's just get going. Let's start with this one, question 1. The sum n equals 1 to infinity of minus 1 to the n plus 1 n over the square root of n squared plus 5. Okay, thumbs up if you think this converges, thumbs down if you think it doesn't. Okay, somebody who thinks it doesn't converge, give me a reason why. Come on, we have a lot to cover. Yes, so does not converge. Because if we look at these terms, if we take, for example, the absolute value of these things, it is indeed just the limit as n goes to infinity of n over the square root of n squared plus 5, and pulling out an n squared from the square root will cancel the n top and bottom, and you'll see that this thing just tends to 1. Are you all happy with that? No? So for very large n, the dominant term at the bottom is just going to be the n squared. We can forget about the 5, so it's just n squared square rooted. So it's, morally speaking, it's n over n. Yeah? Cool. So this limit is 1. So if the absolute value has a limit 1, then for sure these terms don't tend to 0. So by divergence test, so let's look at this guy. This one was A, this one was B. What about this? The sum from n equals 1 to infinity of minus 1 to the n plus 1 over n over 3n to n factorial. And the question is, we want to have more information. We want to know if it converges, and if you think it converges, does it converge absolutely or does it converge conditionally? So recall our picture. If this blob denotes everything that converges, there is a strict subset of things that converge absolutely. It's a stronger condition. Yeah. And those guys around the outside, these things we call conditionally converging. So things that converge but do not converge absolutely. So these guys here, this is conditional convergence. Okay. And this entire blob denotes everything that converges. So somebody give me an example of a conditionally convergent series. Give me an example of a conditionally convergent series. Excellent, good. Now, can you think of an example of such an alternating series? What about this? Is the blue visible for you? Is it okay? Okay. This, for example, let me run this conditionally convergent. Yeah, we take the absolute value, it's just 1 over n, that definitely doesn't converge. But this thing does converge, because recall, for an alternating series, all we require is that the terms go down to 0 and go down monotonically. In other words, each term is less than the other. Okay, since we're doing recap, let me add that as well. So recall, if we take this thing, which is the alternating series, then converges if bn plus 1 is less than bn, and the limit as n goes to infinity, bn equals 0, right? Cool. All right. So this, for sure, we're going to be asked about. This is basic stuff. This is basic stuff about series. You should know what absolute convergence is. Should know what conditional convergence is. Should be able to identify examples of things that converge absolutely or converge conditionally. Okay. And the classic example is just something which is an alternating series. Yeah? Okay, so look at this guy. Does it converge? Thumbs up. If you think it doesn't converge, thumbs down, and then I'll ask you what kind of convergence. Okay, firstly, does it converge? Thumbs up if you think it converges absolutely. Thumbs down if you think it converges conditionally. So yes, when you take the absolute value of these terms, so look at this. Consider this. The absolute value is just, okay, let me just write it out. Maybe it's obvious, but let me just write it. So the absolute value is just this. Yeah. And indeed, if we look at this, then we have things at the bottom that are growing incredibly fast. We have 3 to the n, we have 2n factorial, and on top we have something which is just getting slaughtered because it's so much slower than the stuff on the bottom. Yeah. So what you said is exactly right. This thing is going to 0 so fast, we expect it to converge. But the tool we use is not the divergence test. Can you think of a tool that would help us? We could use a limit comparison test. We could compare it to a beautiful series. Do you have any beautiful series in mind? Yeah, we could try that. This is very helpful. Thank you, people who are telling me your thoughts. If I agree, it's going to 0 very fast, as is 1 over n factorial. But if we look at this, it's actually going a fair bit faster because we also have this 3 over n, right? So if we try and compare the terms, so look at this. Try to marry with 1 over n factorial. Yeah, so we're going to take this stuff and divide it by 1 over n factorial. So it's the same as taking the limit as n goes to infinity of n factorial times n over 3 to n factorial, right? This is the same as this guy divided by 1 over n factorial. Yeah? Give me thumbs up if that makes sense, otherwise I put the details there. Give me thumbs down if you want details. Okay, everybody seems cool. So this thing, yeah, is the limit we're trying to understand. But if we look at this guy, then what happens? Well, 2n factorial, put it over here, 2n factorial is 2n times 2n minus 1 all the way down to n, and then we have n minus 1 all the way down, right? So it's actually like this. It's like 2n minus 1, oops, dot, n plus 1, And then we have n factorial multiplied by it. Yeah, you see what I mean? Thumbs up if you do, thumbs down if you don't. Okay, so what happens, we can cancel this n factorial on the top, right? We can cancel this n factorial on the top, and we'll have the limit as n goes to infinity of n over 3 to the n, and then we'll have all this stuff here. So we'll have 2n to n minus 1, dot, 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 all the way down to n plus 1. Yeah? And if we look at this, then we still have this thing is being massacred, right? So 3 to the n is way faster than growing than n, and this thing is also very, very big, right? So this thing has got limit 0. So we can't say that these guys are married. Yeah? There's no marriage here. We've chosen the wrong beautiful guy to marry this to. Yeah? So we could either try and find another beautiful guy, or we can do another test. So let me write this again. So look at this. So 2n factorial is 2n, 2n minus 1, 2n minus 2, and so on. Yeah, it just goes down and down and down. And if we keep going down, then ultimately we're going to get to n plus 2, n plus 1, and then it's going to go n, and then it'll go n minus 1, n minus 2, and so on, all the way down to 1. Yeah? That is what 2n factorial looks like. And, whoops, not here. The product of all these last n terms is exactly n factorial. So there isn't any kind of way to pull out, there's no algebraic pulling out of a factor of 2n or anything like this. It's, you know, the only nice algebraic fact we have is just this one, that we have a product of these numbers times n factorial at the end. Well, they have a similar behavior in the sense that they're both going to 0 pretty fast, but the key relationship is so what's the relationship between the two things you suggested? Yeah, so this is the relationship, right? Yeah, cool. And we know what this thing is like, right? Because we did this expansion of what 2n factorial is like, right? So it certainly contains an n inside its expression, yeah? Yeah. In fact, we can just consider, look at this. So we have 2n, 2n minus 1. All of these terms here are bigger than n, right? All these terms here are bigger than n. Yeah? Yeah? And how many of them are there? There are this. There are n minus 1 of these terms, right? There are n minus 1 of these terms before we get to n. Yeah? So, this thing will itself be less than 1 over n minus 1 times n. Yeah? Because we're just writing out the expansion for this, and then we're killing off the n from top and bottom. And we know that when we just get rid of this, we have at least n minus 1 terms that are bigger than n. Yeah? And this thing we know will converge, right? Because this is a telescoping series, or just compare this to 1 over n minus 1 squared, which we also know converges when we start summing from n equals 2. Yeah? Is that making sense? Thumbs up or thumbs down, people. Give me feedback. Okay. Oh, I just counted up the number of terms which are bigger than n. So I'm making really crude estimates. So this term is bigger than n. This term is bigger than n. This term is bigger than n. All these terms are bigger than n. This one is 2, this one is 2. Yeah? Yeah? And how many of these guys are there? There are n minus 1. Maybe there are n minus... If there were, I don't have to worry about exactly how many there are because I'm so much winning, I'm in so much in a strong position. So I don't have to have exactly how many terms there are. For example, I know that there are at least n minus n over 2 of these terms. Yeah? So if I just use that estimate, then I would put 2 over n squared, and that would also be fine. Huh? So I'm just digging into the structure of n factorial. All right, so your suggestion works, but we have to look a little bit carefully at n factorial. Let's try something else. Try and find something simpler to compare this thing to. Try and find something simpler to compare this thing to. So the moral is it's going down to 0 so fast, we can show that it's less than something going down to 0 fast enough to converge. Look at this, find something else simple to compare it to. I claim if you look at this, you're going to see something simple that you can compare it to. What can you see? Perfect, yes, look at this. If we compare this to 1 over 3 to the n, what happens? Well, this is definitely the case, right? Because if we look at n over 2n factorial, then this is definitely less than 1. Yeah? Yeah, because as we see, 2n factorial is a massive growing number, and it certainly includes n in itself, right? Yeah? So we have this thing for free. And that's a lot easier than what we just did over there. Do you see what I mean? Give me thumbs up, people. This is important. I want you to find the simplest way all the time. Give me a thumbs down if it's not clear. Okay, good. So that observation is enough for us because we know this thing converges. It's a series of positive terms, and that's it. So by comparison test, the sum of n over 3n 2n factorial converges, and therefore the series converges absolutely. Let's call this guy here star. This is perhaps new for many of you, but I claim that this is a lot easier than many of the things we learned previous to this section on series and sequences. Yeah? All you need is a feeling for what is happening to these terms. You need to have an understanding of these basic principles, that if it's a series of positive terms, it has to go to 0 fast enough. And if it's an alternating series, we don't care at all. It just has to go to 0 in a monotonic way, that bn plus 1 is less than bn. Yeah? And with these two principles, and then just common sense, this inequality is rather easy once you see it. Yeah? You can answer a lot of this stuff. Yeah? Okay. So that is a way to answer it. We can also, as some of you suggested, do the ratio test. And indeed, what would be a good thing would be to have multiple ways to get an answer. And the ratio test is a good thing to try whenever you have an n factorial. Because what does a ratio test do? It allows us to detect if something is going down to 0 at the speed of a geometric series or faster. Yeah? And this thing, because the n on the top is kind of insignificant to everything else, we would expect it to go to 0 faster than a geometric series. In fact, that's exactly what we've just shown here. Yeah? That's exactly what we've just shown here. So if we do the ratio test, if we do an plus 1 over an, what do we have? We have an plus 1 over 3 to the n plus 1 over 2n plus 1 factorial, like this, over n over 3n plus 1, oops, 2n factorial. And I'm going to have to erase some more space. Okay, give me a second. Okay, so let's analyze this guy here. So this thing, let's call this thing star. Star is what? That is the same as having n plus 1, 3 to the n, 2n factorial, and on the bottom we're going to have n, 3 to the n plus 1. Oops. Like this. Yeah? Because we just take this guy and flip it upside down, and then we get this thing like this. Yeah? Just algebra. And then we see what simplifications we have. So we're going to have some cancellations in terms of the 3. So we're going to have n plus 1. Actually, I'm going to write it like this. And we're going to have a 3 on the bottom here. And then we're going to have this 2n factorial here. And then on the bottom, we're going to have 2 times n plus 1 factorial. So it's 2n plus 2 factorial. Yeah? This, let me put this like this, 1 over 3. So this n plus 1 over n, we know the limit is going to be 1 as n tends to infinity. So we need to understand what this thing is. And if we look at this, so what is 2n plus 2 factorial? It's equal to 2n plus 2, 2n plus 1, and then it's 2n, and then it's 2n minus 1, and so on, right? It's very useful to get familiar with factorials because we're seeing them a lot, right? It's all the way down to 1. And if we look at all these terms here, from this thing onwards, yeah, that is just the same as 2n plus 2, 2n plus 1, 2n factorial. Yeah? So this thing here, 2n factorial over 2n plus 2 factorial, we have a big cancellation. We just have on the bottom 2n plus 2, 2n plus 1. Yeah? So this thing, star, becomes 1 over 3, n plus 1 over n, 2n plus 2, 2n plus 1. I think this is how the solution was done in the book, in the notes. And we take the limit of this. So the limit as n goes to infinity of star is just going to be 1 over 3. This thing tends to 1, and this thing tends to 0. So the limit will be 0. Yeah? Cool. Okay, this is some algebra. Give me your thumbs up if you're with me here. This is applying the ratio test. So this is the ratio of these two terms here. So we should take the absolute value. They are positive, but we should take the absolute value. So this is the an plus 1, and this is the an. Yeah? So what does the ratio test say? It says that if the limit exists and is less than 1, and it converges. So we get the same answer. But this was way less work, right? This was way less work. There's the potential to get something wrong here, make some algebraic mistake, get the wrong answer. In this case, there's almost no algebra. All we notice is that n over 2n factorial is less than 1. If we look at, we could even do this. Look, if we look at n over 2n factorial, then since 2n factorial is bigger than just 2n, less than n over 2n, right? Which is less than a half. Yeah? So if we did like this, we'd have this like here. Yeah? So, faster and better to look at the terms themselves. Exactly as some of you told me, this is going to 0 very fast. Let's try and show it's bounded above by something that's going down to 0 very fast itself. What's the simplest thing we can do? Just compare it to 1 over 3 to the n. And that's it. That's it. So we first tried the limit convergence test. Sorry, the limit comparison test. And we couldn't do it. That was too strong a tool. We couldn't find a nice guy to marry it to. We tried something simpler, the comparison test. That worked. And then the standard thing to do when you see a factorial is to apply the ratio test. And that worked too, but it was longer. Huh? But you would have all got there with the understanding that these things are going to 0 very fast. You all knew it converged. You would have all ultimately come to the right answer, one way or the other. Cool. Everybody happy with this? Thank you very much for those of you who are... Okay, let's do some more. How are we for time? Almost out of time already. All right, as normal, I'm going to do at least one more example. I want to do an example of using the error estimation, which is the most subtle thing we've learned about this. If you need to leave at any time. Please watch the video for this extra content afterwards. All right. So there is question 3. Let's make sure we're making the hardest choice of. Determine the minimum number of terms of this series, the sum n equals 1 to infinity, 1 over n squared, that must be summed so the remainder is less than 0.005. Okay. Solution. So I like these remainder theorems because this is a kind of sign of how things are going as you learn more advanced maths. You have less and less situations where you can exactly calculate the answer. But being able to approximate the answer with arbitrary precision is just as good for all purposes. And this is one of those problems, obviously. So it's pretty hard to determine exactly what the area of this convergent series is, right? In some cases with some particular methods, and there are other methods, more sophisticated methods than we've taught you, we can actually do this. But generally, it's a hard problem, right? If it's not a telescoping series or a geometric series, this is quite a hard thing to do. Yeah? But this could be some meaningful quantity that is actually the thing you need to understand to build your bridge, to understand your heat tolerance of your heat shield or whatever. This is actually something which could be quite critical for some situation. Yeah. So we can add this up any finite number of times. You can write a code, we can write a program that every loop just adds up 1 over n squared, right? That's easy to do. And you can just watch it run, and it seems to go towards some answer. Yeah. We'd like to know how close the answer actually is, because that might make the difference between failure or success of the thing you're trying to do. So we visualize what's going on, right? We visualize what's going on. This is our series 1 over n. So this guy is 1. This is 1 over 2. This is 1 over 3, and so on. Yeah. And we create the function that recovers this series. So let f of x be 1 over x squared, then f of n equals 1 over n squared, yeah? And then we draw this information on the picture. So when n equals 1, we have 1 like this. When n equals 2, we have 2 like this. Start again, start again, start again. Oh, and I'm doing this, you're right. This is squared, and this is squared. So when n equals 2, we have 1 over 2 squared, so we're here. When n equals 3, we have 1 over 3 squared, which is here, and so on. So this function looks like this. We draw the information. We draw the meaning of this thing as a picture, which is what it actually, that's what it actually means. Yeah. So this is our function f. Yeah. And so let's blow up what is happening here. Let's say this is the nth term. So this is n. Let's blow up what's happening here on a bigger picture. Okay. So this is our guy n. The next guy is from n to n plus 1. The next guy is from n plus 1 to n plus 2. The next guy is from n plus 2 to n plus 3. And so on. Yeah? And this is our function that is doing this. Yeah? Now if we want to find out how close the partial sum of the first n terms are, so Sn is little n, is the sum from k equals 1 to little n of 1 over k squared, right? Then the difference between the actual sum, so let's call this thing S, is the sum from k equals n plus 1 to infinity of everything that's left, right? Like this. Yeah? Let's put that on the picture. Put it on the picture. So this is the first n blocks. Yeah? This is 1, 2, 3, 4, and blah, blah, blah. This is n. Yeah? And all these other guys are when we go from n plus 1 onwards. So this is this other guy, this is the other guy. Put this on this picture. This is the blocks that we are counting in this expression here. And we call this the remainder, right? And we write Rn, it's the remainder. It's what's left, right? It's how far we are from the actual answer when we take the first n terms. Yeah? And we sum the terms up to n. Yeah? Cool. So, look at this. What we want to do is to estimate this thing from above. I want to estimate this thing from above. And what does this represent on this picture? This thing represents the area of all of these red blocks. Okay. Cool. So, what can we do? Look at the picture, tell me what we can do to estimate what Rn is from above. Indeed, right? We see from this picture that if we integrate from n to infinity, then all of these guys that we're trying to estimate live underneath the graph of the function from n to infinity. Yeah? Yeah? So, from the picture, we have that Rn is less than the integral from n to infinity of this thing, x squared dx, and that thing we can calculate. It's the limit as r goes to infinity. To r, the antiderivative of this thing is minus 1 over x. So this is the limit as r tends to infinity of minus 1 over r, minus minus, which is plus 1 over n. As r goes to infinity, this is just equal to 1 over n. Yeah? So we can precisely calculate what the area underneath the graph is. Yeah? So Rn is less than n. Yeah? Cool. That's powerful information, because what is our question? Our question is, how many times do we need to get to within error less than 0.005? Yeah? So let's rephrase that in the question of maths, in the language of maths. So in language of maths, our question is exactly, what n do we need for Rn to be less than 0.005? What we've done is rephrase the question in the language of maths, yeah? Yeah? But now we have information about Rn. Yeah? We know that this guy, damn it, is less than 1 over n. Is less than 1 over n. Yeah? It's less than 1 over n. This is what this thing says here. Yeah? So that's the same as saying, what n do we need so that 1 over n is less than 0.005? So let's think about what 0.005 is. Look at this. So 0.5 is just 5 over 10. Yeah? 0.05 is 5 over 100. So 0.005 is 5 over 1,000. Yeah? So this is implied by having that 1 over n is less than 5 over 1,000. If we have that 1 over n is less than 5 over 1,000, then we have exactly what we want. Everybody with me? We want the error to be less than this thing here. And we know that the error, Rn, is less than 1 over n. So we need this to be true. Look at this. This thing, if this is true, if we find n such that this is true, then by this fact here, this implies that Rn is less than 5 over 1,000, which is exactly the thing that we want. Yeah? So I've just written the same thing here. So this implication is exactly what I've just written here. Yeah? If it was greater than, then that's easy to satisfy. If we have 1 over n is bigger than 0.005, then we can take n to be 1. That's true. And that's clearly not the right answer, right? This thing we can just rewrite. Look at this. So 1 over n less than 5 over 1,000. Let's flip things around. That's the same as 5. 1,000 over 5 is less than or equal to n. Yeah? What is 5 over 1,000? So 1,000 over 10 is 100. So twice that is 200. So that's the same as wanting that 200 is less than or equal to n. Yeah? So when we take n equals 200, then we'll have the error is less than 0.005, and we are good. So if you're writing your code and you want to use the minimum computer time, then you need to run the loop 200 times, summing 1 over n squared each time to get the answer to within this very small error. Okay, thumbs down if you're not, thumbs up if you are. Cool. All right. So the key thing is to be able to write this estimate, which is this estimate here. And all this is this picture. This is just, in the language of maths, this is just this picture, and the fact that we can actually calculate what this is by the fundamental theorem of calculus. This is the power that we have. So this is exactly this picture. Yeah? This is this. Yeah? Nothing hard, nothing mysterious, nothing you have to guess. So many, many times when I've been grading exams like this, I will see somebody integrating from n plus 1. And I assume it's because they have in their mind that we have the error estimation for alternating series and we know that it is less than the bn plus 1 term, so this n plus 1 is in their mind, and then integrate from n plus 1, and that's the wrong answer. That is smaller than integrating from n. Huh? Huh? But if you have this picture in mind, there's no way to make that mistake. Right? There's no way to make this mistake. You will see where you have to integrate from, and this is what I want for you. I want you to draw this picture. Don't want you to memorize this as a rule. Don't want you to. We have a cheat sheet. Write it down if you have to, but I don't want you to memorize stuff. I want you to have pictures. And this picture is easy. This picture you can see. Yeah? And this picture is just blowing up what we had here. So let's ask ourselves what we need. We need to see what is left when we keep summing from n plus 1 onwards. Yeah? And that's all. All this stuff is straightforward if you translate it into pictures and draw what you see. Yeah? Cool. All right. So that is it for today. I have office hours now. Stick around if you have any questions. Otherwise, I will see you all on Friday. Have a good day. Bye-bye, people.